All right, welcome. In this video, we're going to take a look at the data structure of B-tree. B-trees come in different forms. They are sort of a generalization of a binary search tree, and they have a couple different uses. And before we get into the actual data structure, I do want to motivate them a little bit by talking about why we might want to design a data structure of this type. So to start out here, I just want to talk a little bit about the different purposes that we might use a data structure for. One sort of standard thing that data structures are for is obviously for storing data, but then why have we stored data there? What is the purpose? Some of the data structures that we've taken a look at so far, stacks, queues, and heaps, for instance, our purpose of putting the data in there is usually to process the data, and usually to process it in a specific order. So stacks, for instance, come in handy, especially say in recursion, of keeping track where we've been to allow us to backtrack to get back to where we started. Often a stack can be very helpful in that. A queue, of course, allows us to sort of process things in a standard sort of first in, first out order, or if we want to add some priority to that, then heaps might come into play. But all of these structures presume that we're going to sort of process the elements in there, in the sense that we're going to add elements into these data structures, but with the intent of at some point removing them from the data structure too. So most of these data structures, stacks, queues, and heaps, begin and end their life cycle in the same way, which is empty. They start out empty, we fill them up. When they're full, that means we're in the process of doing something, and then by the time they're empty, that means we're done all the tasks that we needed to do, or we've searched the data structure we need to search, whatever it was we were doing. Once they're empty, we're done, and we sort of discard them. Okay, so that's not true maybe for every purpose that you're going to use one of these data structures, but a lot of the time that's sort of the assumption. We fill them up and then we empty them. And because of that, there's a few things we might or a few assumptions we might make in our analyses, like we're probably going to do about the same number of adds and deletes, or we should expect the same number of adds and deletes, where in other data structures that might not be the case. So I've got sort of a little rule of thumb for some of these data structures, sort of what goes in must come out kind of data structures. And there's more than just these kinds. We looked at the Huffman algorithm for encoding, and in the Huffman algorithm we create a tree, but again, that tree is sort of transient. It's just there for the moment. We use it to process some data. Once we have the codes out of it, we throw it away. And that's sort of the same idea here. So we don't really empty it afterwards, but we fill it up and then we just sort of throw it away. Some data structures are like that and others are not. So if you're not like that, then my next suggestion here, so some lists, maybe just a standard array or linked list, these type of lists, we might store data there for different purposes than just draining them out again. Binary search trees. We've taken a look at them. We really didn't talk much about why would we put certain data in a binary search tree. Well, the idea is, well, it makes it easy to search. That's the whole point, right? So the binary search tree is not necessarily used like a queue or a heap to sort of keep data while we're processing it. It's there to keep data for a longer period of time. And so I sort of indicate here, and I'll maybe add the last data type, a map. These types of data structures are used more commonly to store data for a long period of time, and then of course we're going to store them in this way so that we can have hopefully efficient retrieval. So we've sort of already seen a transition as we move from list to binary search tree. We change the cost of searching for an element in a simple unordered list with nothing fancy going on there. Searching for an element is going to take us order of n, or big O of n, operations to find it. With a nice well-balanced binary search tree, we reduce that search cost to order of log n. And so this is probably helpful for us if we're moving from, say, a set of elements that we need to search of size 100 to one of size maybe 100,000. If we move up to that size, we're now getting to a size where using a binary search is going to certainly be more efficient, or a logarithmic search will be more efficient. Well, the next step up, and we'll see this in a future video, we won't see this today while we're talking about B trees, but in a future video we'll look at a hash table or a hash map, which is going to again reduce that cost of searching from log n down to actually constant time with some good assumptions. And so if we can do that, we sort of now moved into a realm where actually the size of the set that we're searching really doesn't matter. If we can access any element, search for and find any element in constant time, then that's the sort of the ultimate goal. And again, stay tuned, foreshadowing for a future video about hash tables. So part of the focus that I want to stress now is that we've kind of moved away from some data structures that are just maybe more transient and used for processing data into data structures that are maybe used to store data for a long period of time. What might that mean? Well, maybe in sort of a slightly more old-fashioned sense, well, maybe it's going to store the data at least long enough for you to do whatever you're doing in the program that you're operating on it. Maybe you're changing records, you're doing something, you want to edit it, and so it will stay in there as long as you're going to be operating on it, and then maybe when you're done you save it, say, to a file or something like that. But maybe a more common and more modern sort of purpose was maybe we're storing data in a sort of a database, and in that sense a database is really, the purpose of a database is to store data for access by users, anyone who might actually need access to that data. And usually that means there's a lot of different kinds of access that you need to permit, and you again, we're sort of in that second purpose. We want to ensure that accessing the data you're looking for is as efficient or as quick as possible. So again, stay tuned. That order one, tantalizing constant time access, is probably what we want. But for our purposes today, we're going to be thinking, okay, what if we again want maybe a logarithmic time access better than linear time, right, with the just a simple unordered list. Then maybe we might have a very large database, and that's why we might want quicker access to it. So a good example of that, I've got a couple examples here. So often our databases are going to have large records. So in this sense, what I mean is the actual piece of data that we're trying to store in our data structure is itself quite large. So if we're just thinking of a simple list, we could have lists of integers, we could have lists of doubles, we could have maybe a list with a character or even a string in it. Now when we start saying a list with a string in it, we realize that's a list with a list in it. And we're starting to realize that what we're storing in that original list, the first list, is getting sort of more complicated. Then, of course, using object-oriented programming, we can imagine storing an object in a list. Well, what's an object? Well, an object is sort of arbitrary. Inside the object, we could have all kinds of things. So in a database, in bank records or student records or your social media account, the actual record that is stored in the database related to that account or that student or that is going to be a very large thing. So your bank records might include all of the transactions that have ever occurred in that account since you created it. That could be years of transactions. Your student records are going to include a whole bunch of information, personal information about the student, financial information relative to, have you paid your tuition or not, and then information, of course, relevant to your grades and what courses you've attended and passed and so on. So all of that information is one large, real, bundled record. And so most of the databases that we're going to be, or most of the purposes that we're going to be thinking about using these data structures for in large databases like this is now we're thinking we need to store large records. Now, what's the point of bringing this up? Well, they take up a lot of space and memory, okay? And potentially we don't know how much space they're going to take up in memory. Like the string, a list of strings. Well, each string we don't know how long it's going to be. How do we handle that? Well, how do we handle that with a list of strings? Well, we don't store the whole string there in the array. We store a reference to the string. So all we have is a pointer to that. And so in the arbitrary case, what we will store is a pointer to an object, and that object is your record, your student record or your bank record or whatever it is you're trying to store there. Okay, again, those records are usually really large, but then what that means, what we're going to store in the data structure in the B tree or the binary search tree or the map or the list is just going to be a reference to that record, so we don't have to store something arbitrarily large that might be taking up a lot of memory. Okay, and again, maybe I'll take a step back for a second again to say why this might be important. Well, say I want to search a list and I want to search it for your student record, and maybe your student record is identified by your name, but in a second we'll see it's probably identified by your ID number is more likely. But say we're searching then, if I had a big list, an array of records where in each chunk of memory I have a full student record, a very large piece of information, and then I would have to maybe search that record for your name and see if your name is the one I'm looking for. Then if I want to store that list in memory, the whole list is going to take up an enormous piece of memory because it's going to have all the student records in it. As we're going to see in a second, that might not even fit in memory, and that's going to start becoming a problem. Okay, so we're going to store instead just a reference to the record in the data structure, in the B tree, in the list, whatever it might be. And then that reference, that pointer, if I find it and I realize, haha, this is the one I want, this is the one with the ID number or the name that I'm looking for, then I will follow that reference and find that big record that I'm looking for, probably stored somewhere else, maybe in a file. Okay, I've sort of mentioned now here, I've been talking about these records, but I said, you know, maybe identify the record by your name. And here what we're going to do is we're going to say that there's usually some piece of information in the record, a privileged piece of information or a special piece of information that we call the key, that identifies, and it should uniquely identify that data. So I mentioned maybe your name. Of course, names are unfortunately not a very good tool to uniquely identify an individual. There are a lot of people that have the exact same name. That's possible, of course, especially for some common names. So you might think, how do we uniquely identify people? And you might think like some bureaucrats and organizers have done in the past. Well, if your name doesn't uniquely identify you, well, then maybe your name plus your date of birth. That's sort of a more modern way. In the good old days, actually, in the past, they said, well, if your name, maybe your name was, Robert or something, and that's not enough. There's too many Roberts in the village. Which Robert do you mean? Well, your dad maybe was named John, so they called you Robert Johnson, and then that was just a secondary criteria to say who uniquely identify which Robert you're talking about. I'm talking about Robert Johnson, not Robert Dixon or Robert Williamson or some other Robert in the village. Well, that of course led to us having more than one name, just so in a village we can identify each other. Well, now in a modern time where we're a little bit further than a village, we don't need to just keep track of 100, 150 people. We need to keep track of 150 million people maybe, all registered, say, as say taxpayers in a particular country. If that were the case, we need something to uniquely identify us beyond just our names. So add our date of birth maybe. It turns out that might not even be good enough if you have 150 million people. Okay, so add to it a few other things. It turns out it's a kind of a complicated task if you're trying to keep track of that many people. And so a very common thing to do is say, fine, I'm going to give up on the trying to find something unique about you that uniquely identifies you from every other one of the 150 million people. Instead, I'm going to assign you something, a number. So, of course, in America, in the United States, where I live, I've been assigned a Social Security number. so that I can use that specifically to identify me as an American taxpayer. And I use that in other places too. I teach at the University of Washington, where I've been assigned a different ID number, and that ID number is again assigned to me. And if you're a student at the university, then you probably have a student ID number that has been assigned to you. I have an account number for my bank. I have a driver's license number. All these numbers that get assigned to us are assigned to us specifically for this purpose, which is we want to be uniquely identified in a database somewhere. Okay, and since names and birth dates and such do not uniquely identify us, we've decided as a convention, well, I'm going to assign you some number. Okay, and of course, it's not just numbers that can serve the role of the key, although that's a very standard thing. If you, of course, have an account on sort of a website, maybe in your social media, then your key that uniquely identify you is actually your username, your login ID. So again, you might have that as a student to help you access your records, then that might be attached to a numerical ID as well. So your key does not necessarily have to be an integer or some numerical value. Okay, so we're going to be talking for the next couple of videos about different types of data structures that might be used to inside a database to store these large records, or at least keep track of the large records so that we might again efficiently retrieve them, right? So we, as I mentioned, we might not be storing the actual records in the data structure, maybe just references to them, pointers to the records, that's fine, okay? But we're using the data structure to organize all these records, so that might be stored, who knows, in a file system somewhere. But wherever they're stored, we're organizing them with this data structure so we can search them quickly and find them quickly, okay? All right, so I think I've maybe mentioned that. We're looking for these key value pairs, and the purpose of a database is to find them as efficiently as possible, okay? So I want to talk a little bit about the abstract data type of a map. So here I want to again highlight or remind ourselves of this idea. What is an abstract data type? How does it relate to, say, data structures? Well, an abstract data type is on the abstract side of the sort of broken line. On the other side is the implementation, actual data structures you might use in a program. But up on the abstract side, in sort of the realm of algorithms, of ideas, of just human ideas and human communication, a map is really just anything that relates this key to the value. So we've been talking about the key and the value in the sense of the database, a more practical purpose. Well, in an abstract realm, we'll say anything that serves this purpose, anything that relates a key and a value, we're going to call a map. And we sometimes also call these dictionaries, because a dictionary is a sort of standard example of a map. And so that's sort of my first example I'll give here, that in a dictionary, the word is our key. That's the unique identifier, okay? And we're going to look up its definition. Now, of course, we already have a problem. Maybe a word is not uniquely identified, say by a string of characters. There might be more than one word with the same string of characters. Well, we'll notice that in a dictionary it handles that in a very interesting way. And maybe when we get to hash tables, we'll see this again. It basically puts all the definitions for that string of characters all in the same place. So one that sort of came to my mind, the string T-E-A-R, tier or tear, those are two different words that are spelt the same way. If you go to that part of the dictionary, you're probably going to see like one, a drop that comes out of your eye, or two, ripping paper, something like that. Those are two different definitions that we would put there, and of course some words might have 6 or 7 different definitions, so we would see that. But again, a dictionary allows us to search quite efficiently for a definition. Now, another thing I'm going to highlight here, because a dictionary is a good example of this, if you would like to find a word in the dictionary, we have an efficient way of retrieving it. That's why we have a dictionary, right? We don't just have a random assortment of words with definitions put into, a folder somewhere, and you have to search through them to find the definition you're looking for. No, we put them in order in alphabetical order and lexicographical order so that we can apply binary search to the dictionary. Okay, so if you've ever had a chance, dictionaries are getting a little bit rare now. You've maybe not had a chance to crack one open. Okay, but dictionaries can be efficiently searched using the binary search. And if I think you haven't had a chance to look at a dictionary, well, if you've ever had a chance to use a phone book, it's probably been 20 years since I've looked in a phone book, but the phone book was sort of the same idea. We build that data structure, the book, so that we can efficiently find phone numbers given some name. Okay, again, same idea, right? And same thing, if you had a common name, you know, if you were Robert Johnson, there were probably 17 Robert Johnsons, and each one, how did we uniquely identify? How did we know which one was you? In the good old days, well, we put your address there too, luckily. So if I knew where you lived and your name, and maybe your middle initials in there too, but then if there were 4 all with the same and I didn't know what your address was, guess how we found out? We just called you until till we found the one we were looking for, hopefully. Okay, again, maybe more modern. These are strange old book things we probably don't use as much anymore. What about web security? So any website you might log into, your school, your social media, whatever, you have your username, and then you can use a map to store your passwords. There are very special ways to use a map to store passwords, so make sure you don't just throw it in any old map. People can read maps. You can look in memory and see everyone's passwords. We don't want that. But we might also store the larger record you might store in the map might be the whole profile, all of your posts and all of your all of your friends or whatever you might have on that social media account. Your university, so again, I already mentioned you might have a student ID key. That would be a key we use to search for your records, your bank. I think I mentioned that as well. And then the map, especially if you're a Java programmer, you probably have that experience already, that a map is usually characterized by sort of these 2 methods here, where we have the get and the set. The set, here I've both sort of just indicated on an abstract level that you use the key to access them, but of course the set is also going to use the value. We're going to overwrite the value. Now that's maybe one thing that's also key here, critical, maybe not key, is that for any particular key that you have, you can only ever have one value associated with it. So this is why it's critical that these keys are unique. That's why we give unique keys to each individual. If, for instance, you have a student ID number and we gave that student ID number to someone else, then their records would overwrite your records. We wouldn't want that. So we have to make sure that every record we want to store has a unique key. Okay, again, that's another reason why we use numerical keys or numerical identifiers to ensure that they're unique. Okay, so this is the idea of a map. And we're going to, again, for the next couple of videos, talk about data structures that are used commonly as an implementation of a map. Okay, so the other thing that's going to be important to our discussion here, or why we might use this, is keeping in mind that these databases then, which are usually pretty large, have to operate inside of the machine, and the machine, of course, uses memory at different levels. So let's do a quick refresher of just the memory hierarchy. So the memory hierarchy is basically all the memory that you can expect to have access to given a modern machine. So most modern machines using the von Neumann architecture are going to have a CPU, a central processing unit, or more commonly today, you're going to have a collection of these, maybe 8 of these CPUs, and these CPUs have inside them, they have the absolute quickest memory you could have, which are the registers. So again, it's pretty low-level programming to be thinking about what's going on inside of a register, but right inside that register you can have very, very rapid access to the memory, and you can perform operations on it as they are stored in the register. So that's the absolute fastest. Of course, there aren't very many registers. It says here sort of a tiny capacity. So what happens is we spend a lot of time swapping things in and out of the registers. And of course, we actually have sort of larger sort of waiting area adjacent to the CPU, which we usually call the cache, where we have, you know, some amount of space to very rapidly have rapid access to swap in and out of these registers. Now, of course, if the memory that we're looking for, if the thing that we're looking for is not currently available in cache, which means we probably haven't used it that recently, it might still be stored in physical memory. Now we're talking about your RAM. Okay, now your RAM, depending on your machine, you probably have a couple gigabytes, couple, maybe more than that these days, you know, 8, 16, 32 gigabytes worth of RAM. Now that RAM, of course, is, what does our RAM stand for? We looked at this in an earlier video. RAM stands for random access memory. Okay, random access memory. And if we remember, what does random access guarantee us? Random access guarantees us that if we access our memory, that's the AM, in a random order, that's the R part, then the cost, the amount of time it takes us to access the memory does not change. It's kind of a weird way of saying it, but what, you know, maybe arbitrary access memory would be a better one. If you access the memory at an arbitrary location, the cost of accessing that is the same, constant. Now, why do we say that? Why do we have to bring that up? Because the cost of accessing memory in other kinds of storage, and importantly, other storage, you know, lower down in the hierarchy, are not that way. Okay, we can not just access any piece of any track on a CD with the same amount of time. We have to move physical elements of a CD reader, the little laser. We have to move it, and we have to rotate the CD to access a different track. Okay, if you remember the old-fashioned long play record players, that's just sort of a slower version of the CD player. Okay, the CD player has something like the arm of the old record player, except on the end on the CD player you got a laser beam, not a little needle. Okay, and just like the record player has a track with little bumps, you know, grooves in the record, in the plastic, the CD has little grooves or dots that have been burnt into the plastic that the laser beam reflects off of. So the same thing, we have to move that little laser beam around to access different tracks on the CD or the DVD or other kind of storage like that. And actually, a hard drive, a good old-fashioned mechanical hard drive, operates the same way, that there's a disk on there that spins, and you know, sometimes when your hard drive's doing a lot of work, you can actually hear it in there doing its work. It's going. This sound is the mechanical hard drive moving things around to get to the position in memory that you want to access. So remember, random access memory, that stuff, the reason we like it is it's fast. Okay, we can access it fast. All right, and well, nowadays it's, you know, it's pretty cheap these days, which is why you can have 32 gigabytes of memory. If you think about 20 years ago, having a small amount of memory actually really limited the types of processing that you can do. Okay, because a lot of time what you wanted to do was stored in cold storage. This is what I call anything other than the RAM, the fast storage and physical memory, is something like your hard drive, or I mentioned CDs because they're slow to access. You know, in the good old days when you had CD-ROMs that were, you know, very common and used more often, there was sort of an arms race in how fast you could spin them up. You know, there was a CD-ROM, then it was a 2 times, and then a 4 times, and then an 8 times, and then, you know, you got a 16 times or a 32 times, and you hear them warming up, and they're like, you know, they're like they're going to take off or something, because, you know, there was a competition on how fast you could access the memory, was how fast you could spin your drive around. Okay. All right, so those aren't the only cold storage. Of course, in the old days, there were other kinds of disks, you know, other types of floppy disks, which have just completely been abandoned now. Well, CDs have mostly been abandoned as well. But now our cold storage is in the cloud. Okay, the cloud is our new cold storage. Where do we want to store things if we don't have space for it on our machine? Well, a lot of stuff we just don't even store on our machines anymore. We'll store it on the servers on the internet somewhere. But accessing that information then is still very slow. Okay, if we now want to retrieve something that's stored on the internet, at the very least we have to wait for it to move over the network into memory, into this part of our memory hierarchy. Now, the memory hierarchy of the internet expands out here. This is the network out here beyond anything local. Okay, so the reason that I wanted to bring up the memory hierarchy and talk about the difference of where we're going to get that information is, remember that we're thinking about databases that are very large. Okay, so for the moment, let's think about a couple of possibilities. A lot of normal programming that you could carry out probably will fit in your 8 gigs or 16 gigs or 32 gigs. It's very rare that, especially if you're a student, you're working on homework, it's very rare that you have a homework that's going to cause you to load 4 gigabytes worth of data. Maybe these days, if you're doing some machine learning or something like that, you might need a lot of data to work on. But if you're doing, sort of list type assignments, you might have a list with 100 pieces of data or 100,000 at most, something like this. These are pretty small. These are always going to fit in memory. So we never really have to think about what's going on outside of memory. Everything, when our program loads up, it grabs a small chunk of memory, say a gig, even if that's a lot, and it says, this is my memory. Everything I'm going to do is going to be in this memory. Okay, so when I say everything I'm going to do is going to hang out in this memory, one important thing I mean is, say one of the things you do is you read a file. Okay, so maybe you're reading in a text file that is like maybe a couple megs. All right, you read in that text file. Well, what you're doing is you're taking the text file, when you're reading it, you're going to your hard drive where it's probably stored, or maybe the network if you're loading it off the network, and you're saying load it into memory, but then you're loading that 3 megabytes into memory, and it lives there in memory, at least for the whole time that you're going to be using it during your program. It lives there in memory. Okay, and so anytime you're accessing it, anytime the CPU needs to do something to it, read it or maybe write it, it has very fast access to it. So here, let's imagine that what you're trying to do is you're trying to operate on a very large database. So the database is, let's say, 100 terabytes. Okay, so that's large enough. It's probably not fitting on your machine. Let's say it's out in the cloud somewhere. Okay, and you want to do access to it. Well, when you're operating on that very, very large database, you can't go and just grab the whole database and put it in your memory. You can't even grab the whole database and put it on your hard drive. So what can you do? Well, here's where our maps are going to come in, our B trees are going to come in. Our idea is, well, maybe what I can do is I can go grab a map of that 100 terabytes. Okay, so not all the records that take up 100 terabytes, but something smaller that maybe can fit in my physical memory. Let's just say for the moment that, let's say we could build a binary search tree of the ID numbers of that very large 100 terabyte database. Okay, not the whole records, but just the ID numbers. We put them all in a binary search tree, and maybe let's say there's 4 billion. I'm going to pick that number pretty strategically, but let's say there's 4 billion records in that 100 terabyte file that we want to, database that we want to access. Well, those 4 billion records that we have can be, maybe using 4 billion ID numbers, could be stored all in a binary search tree. Okay, now how deep would that binary search tree be, and how much memory would it take? Well, I'm going to do a couple rough estimates here. Okay, let's say I said 4 billion. Let's say that each of the ID numbers we're going to use is going to be a 32-bit integer. Now I picked 4 billion because we can fit 4 billion ID numbers in 32-bit integers. So good. Okay. So we have a 32-bit ID number. So we need to store that on our binary search tree. And then I mentioned we also need to have references, records that are we're gonna have to have some pointers to those records, the 100 terabyte that's maybe stored on the record. So some address. I'm gonna assume for the moment that's also 32 bits. It might be more, could be 48 bits, 55 bits, 64 bits, something, We could imagine it being larger, but for the moment, for ease, I'm going to say that's also 32 bits. Okay, so we have these 4 billion things, we have 32 bits of ID numbers, and we have 32 bits of references to the records, and we need to put that into a binary search tree. Well, 32, that's 64, okay, and so again, we can do a little bit of math here. That's 2 to the 6th. My 4 billion is about 2 to the 32. So it looks like the sizes are going to be about 2 to the 38 is about how much memory we're going to use. Okay, or let's see, that's about 32 gigabytes if my math is right. Someone can back me up. I might be off by an order of magnitude. My brain math sometimes is off there. But let's say that's 32 megabytes. Let's say if it's not, you need 64, I said megabytes, gigabytes. So say we need 64 gigabytes, then go ahead and buy yourself some more memory then. Okay, if we could then we can fit the whole binary search tree I've just imagined in my mind, we can fit that whole thing in the memory. So now, say I want to search for my record, I don't actually need to go and load that whole 100 terabytes into memory one chunk at a time, slowly trying to access that. Instead, what I can do is load this one binary search tree into memory all at once. Sounds like it's taking up all my memory, but we'll worry about that in a second. Okay, so let's say I load that whole thing all in my memory all at once. Then I can search that binary search tree for the pointer to the record that I want. And maybe all I need to do as a database manager, so maybe the purpose of my program is just to allow anyone to use it to find the record they want in that 100 terabyte file. Well, all then you really need to store in memory is this binary search tree. And you can use that. And actually, my little math in my head, with the 4 billion records, with a binary search tree, log n is about 32. So that's pretty fast access if you are searching this very large file for your element. Okay. All right, so again, this is that idea. Now I mentioned I pushed one more problem off. I said if we load that whole binary search tree into memory, then it might take up all our memory. And normally our operating systems are not going to let us do that. They're going to say you don't get that much. You only actually get 1 gigabyte at a time. So the whole idea of storing it all in this smaller binary search tree just with ID numbers and just with references, that whole idea is maybe thrown out the window if I can't put the whole thing into memory at once. So what happens if we can't fit the whole binary search tree in memory at once? Now again, there's two possibilities. One is I don't have enough memory, and I said earlier, well, just go buy more. Well, that stops becoming efficient at some point. Okay, at some point, we can't just buy more memory. So we still have to face off this problem, and the reason is this problem could also occur because I said, hey, imagine we had 4 billion entries. Well, what if we had 4 trillion entries? Well, now, the math didn't work out so nice anymore. We definitely need, the binary search tree is so large it's not going to fit in physical memory without a huge upgrade. So let's say, okay, maybe I can only store part of the binary search tree in memory at any one point in time. That's where things get interesting. Okay, we can only store one part at one time. So how much can we store? Well, let's say our memory choice is so limited that we can only store maybe a node or two at a time. Okay, but that node might be pretty large. We could store a pretty large node. Okay, and that's where the idea of a B tree is going to start coming in. Okay, the idea behind a B tree is saying maybe we had, and again, B trees are kind of old, so modern memory, 32 megabytes, we're thinking of something pretty big that needs to fit, 32 gigabytes, something has to be pretty big to fit in a 32 gigabytes, fill it all the way up. Well, go back to when it was 32 megabytes, okay, or something much smaller like that. Filling up that memory happened real quick, and we still had databases back then that needed to be managed. So we need to solve this problem. So the idea behind the B tree is the idea that maybe you could only store a small chunk at a time while we're going to design our nodes to fit in these small chunks, whatever these small chunks are. Okay, so I've sort of been talking a little bit about a kind of computation that we call external computation. This is where the data structure that we're computing on will not fit inside of our internal memory. I mentioned this mostly happens when we're working in a large database, at least in modern times. And external computation will sometimes come up with different algorithms. Say we had a large list that couldn't be fit in memory and you need to sort it. What sorting algorithm is going to be most efficient at doing that? Okay, and I'll leave that as an exercise, a guess. And then what we're really focusing on here is we have data structures that are designed for external computation, like B trees and hash tables, and well, specifically, dynamic large hash tables. Sometimes a small hash table might not have to face this problem, but a large one might. And then the main thing that I want to focus on that I realize I haven't really highlighted yet is that when we're computing externally, the main problem, and just going quite back here, is we need to move memory, we need to move stuff from our cold storage, whether that's our mechanical hard drive, our network, or whatever, into physical memory. And when we do this, this process of moving from one storage to the other, we call paging. Okay, and the reason we do that is because the chunk of memory that we copy over is called a page usually. Actually, it has a couple different names, but a page is usually what we use to call the piece of memory, the chunk that we're copying over. And we often say we're copying it into a frame, a memory frame, which is where it's being stored. So sometimes you'll at least hear these words maybe being used, at least they sound like they're being used kind of interchangeably. They're not, they have subtle differences, but we might talk about the page size or the frame size at the same time, because the size of the frame determines the size of the page that we're going to copy into it. Okay. Now the other thing that maybe I should highlight here, one of the reasons why we copy pages at a time, maybe just going back again, is that remember that our physical memory has random access, which means where we're copying it into in physical memory, it doesn't matter where we're copying it to, because we can copy it to any place with the same cost, okay, the same amount of access time. But the other non-RAM storage, okay, where we do have a cost to access different pieces depending on where we were before, okay, in a record player or a CD, it's the easiest to play the current song from where it is, because we just keep spinning and let the laser stay sort of lazily where it is, or the needle where it is on the record player. Likewise, in a hard drive, to read the current track, meaning reading the current chunk of data that is on there, is easier than moving around, moving to a different place. So we like to read a big chunk at a time. We don't want to jump around all the time. We'd rather read a big chunk. So that's why our operating systems and our hard drives and other pieces of memory and buses and so on are optimized for us to move pages at a time, where pages are larger chunks. So let's just think for a second what this means. So if you have a simple program like you have right now, maybe, and you want to copy, you want to open up a very small file, say it's a text file, it's only a couple kilobytes, something like that. You open it up, and when you open it and read it, there's going to be your operating system is going to say, okay, that information does not exist in memory, so I need to transfer that file wherever it's stored on the hard drive into memory. But it's not maybe going to just go look for that real small chunk that you're looking for. It's going to find the chunk of memory that contains that and swap that into memory, and then give you access to the part that you want. Because copying the whole chunk it takes just as much time as copying the small piece that you're actually asking for. So we're going to copy the whole chunk in, because the operating system really doesn't know what you're doing, and honestly, we don't know what we're doing half the time too. So the operating system is saying, look, I'm going to copy this whole chunk in, hoping that if you're going to use some other piece of memory in that chunk in the future, I don't have to go back and copy it again in the future. I've copied the whole thing. And there's a sort of a rule of thumb, or there's a little bit of just some intuition there saying, hey, if you're already accessing this part of the hard drive. You might be accessing this part of the hard drive again in the future. So let's just grab a whole big chunk at a time. Okay. So when we're paging, when we're swapping this memory from cold storage, a hard drive, or the internet or somewhere into memory, we're doing it in these larger chunks, and sort of a standard size that you'll find for a lot of operating systems is these are 4 kilobyte chunks, or about 4,096 bytes, okay, which is a pretty big chunk. Okay, for instance, that certainly could contain a small record that just has text in it. Okay. All right, so again, depending on your operating system, your machine, and how you have things set up, you can change this. And when we're talking about databases, that this would be certainly a purpose for us to maybe change our page size if we have, say, a really large database where we're going to want to have larger pages. Okay, why might we want to have larger pages? Well, as it says here, for data structures that are optimized for this kind of computation, we usually try and have our nodes fit on one page. So there's sort of two ways we can do that. We can start with the idea that imagine our page is 4,096 bytes. Okay. Now imagine our node. We get to pick how many elements go in our node. That's something we're going to see in a second here. When we pick how many elements go in our node, we want that many to fit in 4,096 bytes. So I said, we were doing a little math earlier where we said 32 bits for an ID number, 32 bits for maybe a memory address. Put those together, that's 64 bits. Well, we could take this 4096, divide it by 64, and that could tell us roughly how many nodes we could fit on a page, roughly. There's a little bit of off by one error in there. But roughly that could tell us how many nodes we could fit on a page, and that's actually quite a bit. We could fit not 2, 3, or 4. That could be, I don't know what it is, 32, 50, 64, 128, something more like that. And that's quite a bit larger node then, okay? And then say a binary search tree, which only has one key in each node. Okay, so I think that brings us right into our definition of a binary, or sorry, of a B tree, which is, again, I've sort of been hinting at it all along here, but a B tree is going to be a generalization of a binary search tree. But what we're going to do is we're going to allow for each node to have more than just a single key. Okay. And so using this discussion that we've had about external computation, that means we're going to allow each node to be as large as it needs to be to fill up one page. Okay. Now again, the reason we do that, what it means is whenever we're spending time going to the hard drive and asking it, hey, we need a new node, we're optimizing it so the hard drive will copy that perfect chunk of size back into our memory, and that thing that it'll copy into memory will be a whole node with a whole bunch of information in it. The perfect amount to fit in that page. Okay. All right, so a B tree, again, a generalization of a binary search tree, developed in the, 72, I think is when it was published. I think it was developed maybe a couple of years before that, but let's say it was published in 72 because that's what my slide says, and I got that off Wikipedia, so of course Wikipedia must be right. But here we've got, this was developed by a couple of researchers working at Boeing Research, which was a pretty active research for computer science research in that time, Bayer and McWright, and they called them B trees, and it's sort of still a piece of computer science mystery why they called them B trees. They've never really told anyone why they're called B trees. There's been hypotheses about why they're called B trees. Maybe they're Boeing trees, so maybe they're Bayer trees, and so on. And of course, McWright, sort of in an epic troll, says, well, if you want to know about B trees, it says the more you think about what the B and B trees mean, the better you understand B trees. Of course, he tells us that without telling us what the B and B trees means. So I think he's just trying to tell us to think about B trees a lot. And of course, B trees get actually used quite a bit, so maybe it was prophetic. So here we have our B tree invariant. And I think I hinted at this, but B trees are sort of designed or generalized off of a red-black tree. And some of you might see that as we go, that there's some similarity. Maybe if there's a point or two where I can see it myself, I'll try and point it out. It's a little obscure at times. But like the red-black tree, it has kind of a involved invariant. The last point here is really our binary search tree invariant, which is just this generalization of the binary search tree invariant. But let's just kind of go through here. I've tried to organize them in an order that I think makes sense. The first one I put first just because it doesn't get violated very often. We design our tree around it, but here the idea is that all of our trees have the same, all of the leaves have the same depth. Now this does come similarly to a red-black tree. Red-black trees don't have all their leaves at the same depth, but they have all their leaves at the same black depth, and that's, we're not going to have red and black in B trees, so we don't have to worry about that, but all the leaves in our B tree are going to be at the same depth. Okay. Okay, now the other thing we're going to have, because our nodes in our B tree are going to have more than one key in them, so in a red-black tree and our normal binary search trees, a single key. And we'll notice if we have a single key, we can have a left child and a right, those that are less and those that are greater. In a B tree, we can have any number of keys technically, but for a specific B tree, we're going to limit them to D, and we call D the order of the B tree. And down here I've got a few examples, and we're going to be mostly working with 2-3 trees, which I would call an order 2 B tree. There are a couple definitions out there that would call that an order 3 B tree, but I'm not going to try and argue about that. But in a B tree, we're going to have at most D keys, and so using that same math we did for the single key case, in a single key we had 2 children, a left and a right. If we have D keys, we're actually going to end up with D plus 1 children. Okay, and this is sort of going to be straightforward, but here I've labeled it with C and C plus 1, but that's just because D is my maximum number of keys I could have. And then also we're going to have a minimum number of keys, which is going to be the floor of D over 2. Now I personally prefer to have order or my D be even so that this no floor is necessary, but we could define B trees for odd orders too. Usually we just kind of ignore them. Specifically, a B tree of order 1 might be a special case, which I think really, in my brain I just want to say, hey, that's just a binary search tree. Depending on how you think about it, maybe it's a red-black tree. But I don't spend a lot of brain cycles on B trees of order 1 that they're not really worth thinking about. B trees of order 2 are the first ones of interest. B trees of order 3 I've really never thought of. B trees of order 4 are the next one that most people talk about. And then when you get into the real actually working with B trees, these two orders, 2 and 4, are useful for talking about B trees. When you're learning about them, if you're a student and you want to learn how a B tree operates, if you're actually using a B tree in a database, like I mentioned, the order is usually much greater than 2, 128, 1024, something like that. If it's much larger like that, then you're probably not by hand trying to figure out how the B tree looks. You're, of course, coding it in some way. Okay, so the 2 keys here, or the two main criteria, are the maximum and the minimum number of keys in a node. Okay, between D and about half of D. Okay, so if we have a 2-3 tree, that's 2 and 1. You have to have at least 1, but you can have at most 2. In a 4-5 tree, that would be you have to have at least 2, or you can have at most 4. Okay, and again, here these are a restriction on keys. There is one exception, which is the root. The root is allowed to have a minimum of 1. And that's just to allow us to handle small B trees and B trees with certain numbers of nodes. Okay, so the keys that we have stored there, now we know we have some limit on how many they are. The other thing we do is we store them in ascending order. So technically, the node itself is what I would call an ordered list. We keep the elements in order in that list. Okay, but of course the list has a constant size, so maintaining that order is a constant amount of effort. So specifically here, if we have C keys, then we might have key K1, key K2, up to KC, and so they would be in ascending order in our node. And again, C in this case would be between our min and our max. And now if we have a non-leaf node, so our node has children, of course, all our leaves have 0 children, and remember, all our leaves have the same depth. But if we have a non-leaf node, so the root or any other internal node, let's say it has C keys, and let's assume C is in that range again, then we know it's going to have exactly 1 more children using that same math that we did before. And so I'm going to call them B0 up to BC. Okay, so B0 comes before K1, B1 comes between K1 and K2, and that's because the binary search tree invariant that we're going to rely on here is that if you have any key K and it's in the subtree rooted at BI, then the value of that key must be between Ki and Ki plus 1. So for the moment, let's just look at B1. B1 is going to be between K1 and K2, K1 and K2. So any keys in this subtree B1 have to be greater than K1 and less than K2. Okay? And again, what that allows for us is to use binary search tree logic to search our B tree. Okay? And again, we're going to do that by saying, say we get to this node and we're searching for the key K. And if we find out that the key K is between K1 and K2, then that tells us we should continue our search at this child, B1. The node B0 is less than B1. Okay, less than K1. And so those are all the smallest values. It has nothing it's greater than, there is no K0. And on the other end, our BC is greater than KC, there is no KC plus 1, so there's no other term. So our 2 edge cases are special, but all the internal cases will have a left and a right key bounding their upper and lower bound. Okay, of course, on the edge cases, the upper and lower bound are either determined elsewhere in the tree or just simply negative infinity and positive infinity. Okay, so these are the rules. And again, this last rule is just the binary search tree logic applied to multiple keys. And the rest of this is just telling us a little bit about how the keys operate. Okay, so as I've mentioned already, we've got an example here, or we've got a couple different kinds of trees that we can use. 2-3 trees and 4-5 trees are usually used as examples when teaching. So we're going to do that here in our video. We're going to focus on 2-3 trees. But in our larger database, usually we want to make sure that our node fits on one page. Okay, so here's my example of a 2-3 tree. So let's just verify my invariant. Okay, so all of my nodes, first of all my leaves on the same level, check. That one, again, is, if you violate it, you know you've done something wrong. Okay, because we're never going to see a tree where that's not the case. So if you violated it, you've done something wrong. But again, I put it first just because we sometimes overlook it. We can definitely see that here. Now, what about the number of nodes in our tree? A 2-3 tree. Now, the reason it's called a 2-3 tree is 2 is our order, as I'm calling it, and 3 is how many children you can have. You can see this node has 3, right? So, you know, order 2 B tree, you can call it that. They're more commonly, just for conventional sake, called 2-3 trees. And if you follow Knuth's definition, of course Donald Knuth is a famous computer scientist, he called the order defined based on how many children you can have. I think that makes the definition a little bit messier, so I've gone ahead and taken it as my arbitrary duty to go and change the order to the number of nodes. But I call this an order 2 tree, and so again we have 2 nodes as our maximum, 2 keys in a node, sorry, as a maximum, 1 as our minimum, 3 children as our maximum, but we could potentially have 2 if you only have if you only have one key in your node, sorry. What else do we see here? Well, we can see that the binary search tree value is maintained here. So we have here this node here, 2245. The node to our left here only contains values, or keys rather, with value less than 22. The one here that's pointed to our middle child has to have values that are between 22 and 45. And then finally, our other node here have values that are greater than 45. So we can see that again, our binary search tree invariant is upheld, but more specifically, our B tree invariant, all of the values are true for this one here. So this is a B tree. Again, you can imagine searching for a value. Say you want to search for 31. You start at the root and you sort of go through this ordered list until you find where it belongs. If you're lucky, you find it in there, right? But if you don't, you find, oh, it belongs between these two. Fine, I will search that child. We get here, we find it. If we didn't find it here, say we're searching for 32, we see it's not in this node, there are no children, must not be in the tree then. Okay, so I'm going to focus for the next little bit on adding to my B tree. So let's take a look at how adding is going to work first. Okay, so if we're going to add to our B tree, the first thing we're going to use is our normal binary search tree logic to search the tree for the, and here's the critical part, the leaf node where it belongs. So we only ever add in a B tree to leaf nodes. Okay. That means if we're searching the tree along the way and we find a node along the way where it looks like it's going to fit perfect, nuh-uh. We go all the way to the leaf and we put it in the leaf even if it won't fit perfectly in the leaf. Okay, only add to leaf. So first step, search the tree for the leaf node where it belongs. Okay, then what? Step 2, put it in that leaf node. Okay, find where it belongs and put it there. Now, this is us trying to keep a couple of our invariants true. One, the searching the tree part is to make sure our binary search tree invariant is upheld. We're only going to put it in the location where it belongs. That's the binary search tree rules. Second, inserting it into a leaf is going to help us ensure that all of our leaf nodes are always at the same level. And we'll see that after we do a couple examples. Okay. However, stuffing it in that node without looking carefully means we might overflow the node. Okay, our risk in adding to a node is that maybe our node already had D elements, so adding K in is going to increase the size to D plus 1. Okay, so this here I say if the size of n is greater than D, well, it should only be D plus 1, because if it goes over D, we go ahead and do a split. Now a split is where we're going to split our node in two, using what I'm going to call NL for the lower half and NU for the upper half. Now remember, all the keys in our node are already in order. So splitting them in two is straightforward. We just grab the lower half and the upper half and we separate them. Now we're going to do this. Now let's remember here that if I've added my K to N and it's greater than D, the size is D plus 1. And also, for the moment, bear with me, let's assume we only have an even D's, so that our D can be split into evenly. So D by itself can be split, or N, sorry, by itself can be split into NL and NU, but we'll have one left over, because once we've added K in, we'll have D plus 1, we'll have one left over, so I'm going to take out the middle element. Now, if we're really lucky, that's the K we've added, but usually it's not. Okay, so we add K in, that's going to inflate N to be D plus 1. Then we're going to find that middle element, and we're going to take off the lower half of the keys, make that one node, NL. We're going to take off the upper half of the keys, we're going to take that node, call it NU, and we have this KM left over. What do we do with it? We recursively insert it above into our parent. What do I mean by that? Recursively meaning that when I do that insertion, I'm back into this step again. I'm doing this add bit, which means I might again have to do a split on my way up. All right, so when I do this, now when I just explained this here, I said imagine my D was even. What that means is we knew exactly that my left half would have D over 2 and my upper half would have D over 2. So I'm just going to say here, imagine if we were odd, well then we're going to have one left over in one of our halves. Okay, so one will be the floor, the other will be the ceiling, but the floor plus the ceiling is still D. Okay, so, or the floor of D over 2 plus the ceiling of D over 2 is still D. Okay, so we see that here, that all this comment here is saying is that we can split our node in this way and have two half full nodes. Okay, neither of them will be too empty. Okay, and then we're going to insert KM above. That's recursive, might do more splitting, whatever. Okay, but also, what if there was no parent? What if we had to split the root? Well, if we have to split the root, we'll just make a new root and we'll split So we'll split the root, we'll make a new root, and we'll insert km above. Now remember, we had the rule that the root could have a minimum of one node. That's for exactly this case. If we split the root, we're going to insert this into a new root, and the new root's going to have only one node in it, so or only one key in it, so we're going to need that. Okay, so the last thing I'm going to do here is just talk a little bit about the cost of this. Well, the cost is going to be the cost of navigating down the B tree to the node, the leaf node that we're adding it to, and then recursing up while we split. Okay, the splits are expensive, but they only do a constant amount of work, like the rotations we saw in binary search trees before. Okay, but so basically the cost is how many nodes we hit on the way down and up, multiplied by a pretty beefy constant. Okay, but that's going to be big O of h, where h is the height of the B tree. Now I would normally say big O of d, where d is the depth, but we've been using d already here for the order, and I don't want to confuse us anyway, so remember the height of the B tree is the same as the depth of the B tree, so this is the same thing. And then the other thing that's important, and maybe we'll get to this at the end, is that the height or the depth of the B tree is also logarithmic. The whole point of all this is to keep this logarithmic. The base of the logarithm, however, is determined by the order d. And so again, when our d gets really big, like 1,000, then our log base gets really big, which means that those values are really small. Okay, so this is again how we add. Let's take a look at some examples of adding that. So let's start in the simple case. So let's add 38. So again, 38 is going to require a search. So we'll start here, we'll search. We see 38 belongs between these two, so we'll find this node. This node is a leaf, so we will add the 38 in, and boom, we do. There's no split needed because there was room there. Okay. So continuing, let's do a different add. Let's try adding 66 now. Okay. Again, 66 is larger than 45. So we can navigate down here. We see it belongs here. Now when we add it, we actually add it into this node and we bump over the 72. This is an ordered list, so we add it where it belongs in the node. Okay. Now we see that that is an overflow of our node. A 2-3 tree can only have two keys in the node. So with 3 keys, we're going to do a split. So in the split, the middle element here, this is our km. The 66. This is going to end up getting recursively inserted above, and we'll see in a second that's going to be a pain as well. But the 56 and the 72, we're going to split those two into their own separate nodes. So we now see the 56 and the 72 have become their own nodes, and the 66 was inserted above with its left and its right children being these two new nodes, the 56 and the 72. Let's just go back one second here. We'll see the old right child of the 45 was this old node. That node actually gets destroyed in our split, right? So this link kind of gets broken. And instead, we insert the 66 above with two children, its left child and its right child being the 56 and the 72. The 56 and the 72. Okay, so we did a split, all right? Now, we recursively added the 66 above, which means now we have to recursively again say, hey, are we too big? And we are, so we need to split. So, here, we just did a split. Take a second, pause if you like. What are we going to look like after the split? Okay? So after the split, again, we're going to take our 45 here. That's our middle element, that's our km. It's going to get inserted above into what? A new root node. There is no node there, okay? The 22 will become the new left child, the 66 will become the new right child, but their children are untouched, so these connections here, untouched, okay? So again, we're going to split the root. Afterwards, the 45 became the new root, its left child was the 22, its right child was the 66, and the 22 and the 66 brought their children down with them. Okay, so in the split, they just held on to those two children. All right, so this is what we call, this is what we sometimes call a cascade of splits. And in the worst case, we cascade all the way up to the top and split the root. And when we do, we increase the height of our tree. So we used to have a tree of height 1 or 2. depending on how we count, and now we have one of 2 or 3. Okay, so in B trees, a common variant of a B tree would be to allow what we call redistribution. And redistribution in a B tree is where we basically shuffle nodes around instead of trying to do a split. So the idea is, before we have to get to a split, if we overflow, before we do the split, we're going to check to see if we can do some redistribution. And redistribution works like this. We're going to look at our siblings, so nodes that we share a parent with, but we're only going to look at our immediate siblings. So if we have more than just a left and a right sibling, we're not going to keep looking and looking and looking. That's just too much shuffling, and it takes too much time. So we just look to our left and look to our right of this node that we're trying to split. If either of those nodes have room in them, meaning they're not already full, then we'll just shuffle some keys over. And that's not as straightforward as it sounds, but it's not very tricky either. Okay. If neither of the siblings have room, like I said, we don't go checking other siblings. We don't keep going on and on. We don't go checking cousins or anything like that. We just stop and we say, okay, fine, we'll do the split. And that's just because checking more than the immediate sibling starts getting too costly. And the reason is because of a trade-off that comes in when we add redistribution. Redistribution is beneficial because it avoids us doing the split operation. So we can avoid doing a split. The split itself is costly in just performing it, but usually doing a split will lead to increasing the height of our tree. So by avoiding splits, the height of the tree stays smaller. And remember, our cost of adding, and as we'll see in a second, cost of deleting as well, is dominated by the height of the tree. So if we can keep the height of the tree as short as possible, then that means all of our operations become less costly. The trade-off here is exactly this, that if we have to check for redistribution and we find out that we can't redistribute, then we have to do the split anyway. We've only added more cost to the split, which was checking for the redistribution bit beforehand. And so every split then becomes more costly. It was already a costly operation. Now it's becoming more costly because we're checking for redistribution beforehand. Again, it's a trade-off because maybe we avoid more of them. Well, it's a trade-off, so you have to see when you're working with B trees if that's something you want to use or not. Let's see how redistribution works now with our current tree. I'm going to add 25 with redistribution. So again, let's do a quick search. Less than 45, greater than 22, belongs in this node, so we'll add it in. Okay. Now, checking our neighbor here, our sibling, we find we do have room. So we'll do a shuffle. Now, I said here the shuffle is not as straightforward. We can't just take 25 and stick it in this node. If we do, it violates our binary search tree invariant because 25 is greater than 22. We can't just put it over here where it's less than. So what we're actually going to do is sort of like everyone in the bed roll over kind of thing. The 25 is going to move up here to the 22, and the 22 is going to move down. Okay, so this is the sort of shuffling down. And in general, we might have to shuffle more, but in this case, we're just going to shuffle this one off. The smallest value here, shuffle off, bump down, and land here. Okay, the 25 moves up, the 22 moves down. A quick little shuffle, no need to split. Okay. It says here, let's try another one. Let's try 33 with redistribution. Well, again, less than 45, greater than 25, it lands here. Adding it in, it bumps everything over. We check our neighbor. Our neighbor does not have any room. We can't shuffle things up into our parent. That's not how it works. We shuffle into our neighbor if it has room. Our parent has room, but that's not how it works. So we do a split. So again, maybe take a moment, think for yourself, what's the split going to look like? 31 is going to go to the left, 38 is going to go to the right, 33 inserted above. 31 a node to the left, 38 a node to the right, 33 inserted above. Okay, so I do want to complete this video, which is a little bit longer video, with just a discussion of removing from the B tree. Removing from a B tree is fairly straightforward because it's kind of the opposite of adding. The operations are logically kind of just the opposite operations, with one sort of asymmetry which comes in with the notion of redistribution. When adding, we redistribute as an option. But when we remove, we redistribute as our first option. The first thing we will do is redistribute to avoid doing costly merge operations, which is the opposite of the split. So let's just maybe quickly go through it and then look at the example. So again, removing is going to start out the same way. Use our binary search tree logic to find the key, assuming it's there. Of course, if it's not there, we're done. Finding it there, we remove it. And again, the risk is that we reduce the size of our node below the threshold. Now, I didn't really mention this when we looked at the invariant, but I had sort of in parentheses that sometimes this minimum is omitted. The reason we might omit this is because of the purpose that we actually use B-trees for, of course, which is, as I mentioned, indexing into databases, so these large databases. And I mentioned at the beginning of this video that these databases are used to store data for efficient retrieval, and it's rare that we delete the data out. We often only delete if there was an error in the data for some reason, we put someone in that didn't exist, something like that. Or occasionally we delete data out because we're about to add it right back in again. We're just sort of reformatting it in some way. And so it's rare for us to sort of delete out whole chunks in our database to get smaller. So it's important for our B tree to grow as it gets larger, but it's not as important for it to shrink as it gets smaller. It is important for heaps to do that, but not for our B tree, because with B trees, a lot of the time we anticipate that after shrinking we are going to immediately grow again. And so we don't want to waste operations shrinking if we're immediately going to get an add that's going to cause us to waste operations growing again. We could get in a case of whiplash where we delete, add, and we shrink, grow, doing really expensive operations when really we should have just left it larger. And so the first thing we do is sometimes we might just stop here at step 2. We might say, who cares if our node got too empty? It's probably going to fill up again very soon. Okay. But let's assume we are trying to shrink. Then next step is redistribution, and it's for the same reason. We don't want to do a merge operation if the next thing we're going to do is split again. So we'll try and redistribute if we can. Okay, say we can't, then we'll do a merge. Now, the way we're going to do a merge is if we can't redistribute, that means one of our siblings must also be almost empty. We've just become too empty. One of ours must also be on a threshold, both of them actually, because otherwise we could redistribute, we could borrow one, right? So we'll take one of our siblings that has not enough nodes in it, and we will merge it. We'll take the KM that joins the two of us together, and we will merge together, the opposite of the split. The split, we split into half and inserted the node above. In the merge, we join two together and delete the node from above. Okay, again, the cost here is the same, just the cost of the height. But let's take a look at a quick example. So the example I've chosen here, again, strategic, is 56 because it causes a little bit of a cascade or a problem here. So again, the first thing we're going to do is find 56 and delete it. Okay. We try to redistribute, so we look to our neighbor. If maybe we're over here, we tried 31, we could borrow the 22 over, right? The 22 would go up, the 25 would come down, right? But here, no such, we can't do that. That would leave this one empty. So that's telling us we need to merge. So we need to merge this node here with this node here, and we're going to bring down the 66. So that actually puts us in this bizarre state. Okay, this node has nothing in it, and this is the child of that node. Well, what that means is now this node is violating its rule. It's now got less than one node in it. So we need to, again, perform our recursive operation. Now remember, redistribution is first. So it says we need to redistribute. We look to our neighbor and it says, yeah, you can borrow my 33. Now let's be very careful here because we haven't tried a redistribution like this before. If we're going to borrow the 33, what's really going to happen is the 33 is going to move up and the 45 is going to come down and be at this node here. And the question really becomes, what happened at this node? Well, this is like a rotation in a red-black tree or a rotation in an AVL tree. This is that middle child that needs to be passed in that rotation. The 33 is moving up, right? Rotating right, it's moving up. The 45 is moving down, it's rotating down. We're passing this 38 over. So we see here that the 33 moves up, the 45 comes down, and the 33 gets passed over. And strategically, this one was sort of in the right spot. Okay. All right, so we're done with that delete operation. Okay. Okay, the last thing I want to do is talk a little bit about the number of nodes that you might find in a B tree. Okay, and let's start with our 2-3 tree. Okay, and in our 2-3 tree, so let's see. So I'm going to just put a piece of data here. So we might have the number of keys in a node. Maybe this is our max. Okay. But we might also have the number of children in a node. And again, I'm going to say max. And in a 2-3 tree, this is 2 and 3. Okay. So now what I want to do is I want to think a little bit about how about the number of nodes on level I. Okay. Now the number of nodes on level 0 was 1. The next level down, if we have a max number of children, would be 3. And the next level down from that would be 9. And we actually did a little bit of math here when we were looking at emery trees earlier. And we saw that this, we could come up, well, clearly on each level then, we're going to have about 3 to the I. So then how about a number of nodes in a tree of depth, D? Okay. Well, at depth D then, we saw that we had to do some interesting math here. We had to do this, it would actually be the 3 to the D plus 1 minus 1 all over 2. Now go back to our emery tree video if you want to find the math for that. This is just using our geometric series, adding all these together, finding the sum I equals 0 to D of 3 to the I, and seeing it's equal to this. Okay. Now we'll notice, oh, and I needed a little extra room here, so let me delete this. We needed, I want to say now, what about the number of keys in a tree of depth D? Well, if this is the number of nodes I can fit in a tree of depth D, and this is the number of keys I could put in a node, I multiply the 2 cancels out here, I just get this number here, 3 to the D plus 1 minus 1. That's how many keys I can store in a B tree rather, of depth D. In my B tree, sorry, a 2-3 tree, a B tree of order 2, as I'm calling it. So what about a 4-5 tree? 4-5 tree is same math, except we got here, maybe I'll do it down here, we got 4, we got 5, so we're going to get 5 to the I here. We're going to get 5 to the D plus 1 minus 1 all over 4, and the 4 and the 4 are going to cancel out, so we're going to get this value here for the maximum number of nodes I can store in a B tree of order 4 with depth D. Okay, and again, it's from this math that we see that we can go the opposite direction. Say now that I have a 2-3 tree, a 2-3 tree, and I have, say, n nodes in it. What's the depth should I expect? My maximum depth. Okay, well, I can use this math here to go ahead and compute that. I can take the n is equal to this, do the, it looks like we're going to do a plus 1 on each side if I want to get rid of that, take a log of each side, looks like log base 3 if I want to get rid of this. That gave me the D plus 1, do a minus 1 on each side, that gives me that. That's telling me my D is equal to this. log base 3 of n plus 1. Ignore my minus 1. Maybe we could ignore the plus 1 if we want to. Okay. Meaning, doing that same thing now for my 4, 5 tree gives me log base 5 of n plus 1 minus 1. Again, plus 1 minus 1s aren't going to matter in the end. In fact, the base doesn't usually matter in the end because all this contributes as a constant out front. But if we care about that constant out front, then this matters. So the last thing that I'm going to leave it at here then is this value here is actually our order plus 1. I was going to call D. I've got D in two different places here, meaning depth and order, and I don't like that. But let me just finish here by saying that say we had we were actually using a B tree and our order was much higher. I'm just going to say, let's say 128. I just picked that kind of randomly. Then this value here, 129, is going to actually be the emery tree that we have. We're going to have a 129ery tree. So the base of our logarithm will be 129. So we would have like log base 129 of n plus 1 minus 1 as the depth of our tree, which when we get to log base 129, our n has to get really big before this gets small. So for instance, our n of 10,000 would be less than 2. Okay, so what this promises for us is that in a B tree, in practice, the depth of our B tree is usually really small. And if we're promised that our n is fairly small, like 10 million, 10 billion, even 10 trillion, the depth of a standard B tree is probably a constant, less than 10. Okay, and that means the amount of time it's going to take you to navigate, remember all the way back to the beginning of this video, talking about databases and trying to work with that really large database. It means the amount of time it's going to take you to navigate that B tree to find the record you want is less than 10 checks, less than 10 accesses of these nodes. And even if each node requires us to page from memory, optimally we've designed it in that way, then hopefully we find it quickly. Okay. All right, so I want to complete this video here. I know it's a longer video, but do come back for the next video where I'm going to practice what we just looked at. So we only looked at a couple quick examples of adding and deleting. In my next video, I'll grab our random numbers and I'll start adding them into a B tree and then probably delete a few after to see what happens. So thanks for watching, and we'll see you in the next video.